Hey, it's Professor Gilmet, and I just wanted to do a new updated video on logical arguments. So that's what we're going to talk about today. And so the objectives for this particular lesson are to determine the validity of a symbolic argument by using truth tables or by using standard arguments. Okay, and I'm going to show you like 8 standard arguments. And then determine a logical conclusion from a given set of premises. So we're going to use a truth table for that. And then, of course, determine the validity of a syllogistic argument using Euler diagrams. Okay, and so that's the end. And so we're going to use some set theory for that. So let's consider the following statements. If it is Wednesday night, and I actually happen to be recording this on a Wednesday, then we will watch Arrow. And so it is Wednesday night. What is the logical conclusion can you draw from these two statements, right? Hopefully you came up with we will watch Arrow, right? And so why is this important, right? So drawing a logical conclusion from a given set of statements is an important application of logic. Also, we use logic in daily decision making after considering all the facts that we know to be true. All right? And so I feel like this is the culmination of all of the other work we've done with truth tables and logic and conditionals and stuff, because we're going to use all of that for this last 2 sections, and I think these are the reason that we should study logic. Because what we want to do is determine the validity of arguments. All right? So in the previous notes, we used truth tables to determine if 2 compound statements are equivalent. And so we'll be using this to evaluate the validity of a logical argument. Okay? So, for example, let's look again at the compound statement above. If it is Wednesday night, then we will watch Arrow. And so P would be, it is Wednesday night. Q will be, we will watch Arrow. And so then that first premise there is the compound statement P then Q, right? If it is Wednesday night, then we will watch Arrow. If P, then Q. And the second premise is P, that it is Wednesday night, right? And so the conclusion we come to is Q. But is this the correct conclusion, right? We can use a truth table to determine the validity of the argument in the following way. And you can check that the following is a tautology. And so if, right, premise 1 and premise 2, those are the 2 premises are true, then the conclusion must follow. So if premise 1 and premise 2 are true, then the and statement will be true. And then the conclusion must always be true. And so we see that played out in the PQ, P implies Q. The combination, the conjunction of that would be premise 1 and premise 2. The conclusion is Q. And so if P then Q and P is true, then Q should follow. And so, again, I have true, true, false, false set up. The true, false, true, false. The only place where the conditional is false is when P is true and Q is false. With the and statement, the only place that and is true is when the 2 are true. I simply copied Q and pasted it here because I wanted to keep a left to right for the conditional that's in this last column right here. And so then following this 2 premises being true, then the conclusion should follow. It does. It is true in all circumstances. And so what we see here is that the truth table is true for every value of P and Q. So these premises, when they are true, do lead to the conclusion that Q is going to be true in all cases, right? And so when P implies Q and P are not true, then sometimes Q is not going to be true. But we got that true for every value in this last table right here, and so that makes us happy. Okay? And so an argument is valid when its conclusion necessarily follows from a given set of premises. In other words, it's a tautology. And an argument is invalid, or a fallacy, when the conclusion does not necessarily follow from the given set of premises. Basically anything except a tautology, right? It doesn't have to be a self-contradiction, just has to be false in one spot. So symbolically, we write the argument like I did above, right? Where you've got premise 1, premise 2, okay? Then you've got a separating line, normally, right? This guy right here. And then below that is the conclusion, and we use these 3 dots, where the 3 dots mean therefore, and then the conclusion, okay? And so the first premise and the second premise, therefore Q. Now, we do have some forms of logical arguments. For instance, once we've demonstrated that an argument in a particular form is valid, all arguments with that same form will also be valid. In other words, every P then Q and P premise will logically lead to Q. And so that is the law of detachment right here. And so that is a general thing. If we can symbolically set it up like this, that will always be true. We also have the law of the contrapositive, where you'll notice that not Q, then not P is the contrapositive. We have the law of syllogism, okay, which is kind of like in algebra, where like P would be equal to Q and Q would be equal to R. So then P is equal to R. So you kind of have that same situation here with the law of syllogism. And then, of course, we have our disjunctive syllogism with the or statement. And this is important, right? Because there were times when we could change or into ands into ors if we negate them. Some conditionals can be written with disjunctives. And so this is a useful tool to have in the back pocket. And then there's the most common fallacy, the fallacy of the converse. If P implies Q and Q is true, then P follows. And this is not true. P does not follow in every circumstance. And so this is not a valid argument. So in that same vein, the fallacy of the inverse, right? If you didn't do P, then you have not Q. Not necessarily, right? Because remember, the converse and the inverse do not have the same truth tables as the conditional or the contrapositive. And so reversing them are fallacies. Okay. So remember, if you're not sure whether an argument with 2 premises is one of the standard forms, or if you do not remember the standard forms, right, you can always determine whether a given argument is valid or invalid by using a truth table. And that was what I did to prove the law of detachment. I actually created a truth table using this requirement for the argument. Okay? So now, what about an argument with 3 premises? Well, with these, we have to use a truth table to determine whether the following argument is valid or invalid. Okay? And so, for example, if there is a crime in Star City, then the citizens are afraid. The citizens are afraid, or Black Canary can try to stop crime. Black Canary can try to stop crime, or there is crime in Star City. Therefore, there is crime in Star City. Well, there's a lot going on here that we need to unpack. And so the first thing that we need to do is translate the sentences. And so what we're going to have is call P, that first statement, there is crime in Star City. The second statement that we can see is after the then, the citizens are afraid. So we're going to call that Q. R is the next statement that we run into, Black Canary can try to stop crime. Now, if you look at the rest of the argument, right, everything else, Black Canary can try to stop crime. We already have, that's R. there is crime in Star City, that's P, and then there is crime in Star City is P again. And so what we want to do is we want to construct the symbolic argument. And so if P then Q, if I have Q or R and I have R or P, therefore do I necessarily have P? Is P true under these three premises? And so, right, we have to use a truth table to determine it. All right, we don't have a standard form for this. So the third thing that we do is we construct the truth table. And so here is my standard 3. And then what I did was I don't have any negations or anything, so I just made each of the 3 premises in this column right here. And so you'll see I use the conditional, I use the disjunctive, and I use the disjunctive again, and you'll see it follows the very familiar pattern. Okay, so I would just filling those in with rules. Now, fourth, we need to determine the validity of the argument. So I have these 3 premises, okay, and so what I need to do is if I look back up here, I see that I need the premises to be anded together, right, as the complete premise of the if statement, and then the conclusion, right? So I've got my premises, all 3 of my premises, and then my one conclusion, right? So I have to and all of these together and then make it conclude the P. So that's what I'm going to do now. Right? So here is P then Q and Q or R and R and P. And so if you've got 3 statements, right, and you're thinking, how do I and all these 3 statements together? Well, the nice thing is that P and Q and R, 3 statements could be put together all at one time. I know I told you not to do this, but this is the one exception that I would make. And that's because when I type in the and statement, I can actually put in P, comma, and Q, comma, and R, all in one set of parentheses and hit enter. And when all 3 of them are true, I'm going to get this true statement. But if any of them are false, right, I'm going to get these false statements here. And so this is the way I would program that. Okay? And so that's what you see, right? You got the true here, you've got a true here, and a true here, and the other places are false. And then, just to keep that whole, this should be to the left, and this should be to the right, especially if you're doing it by hand, I simply copied P and pasted it all the way down. Right? And so what you can see is where all of them are true and P is true, well, that's going to give me a true statement in both of those places. And where these are false but P is true, I did get a true conclusion, so I'm okay there. But the problem is I have a true with a false, and so now I have a false in these 2 places, and now I don't have a tautology. There are places where the premise is true, but the conclusion is false. And so now we see that the argument is not true and the conclusion is a fallacy, not always true under the given premises. Okay? And so that's how you would do it with a truth table. This is a big truth table. It's 3 statements, and I had 3 premises, so that's why it's so big. I also repeated a couple of columns so that I could keep it the width of the paper. Obviously, if you're using Excel or if you just turn your paper sideways to make your truth table, you wouldn't have to do that. But it's tedious, okay? So now what we want to do is determine a logical conclusion. So if you see a logical argument that follows one of the forms above, then you can find the correct conclusion. Otherwise, it's very hard. This would be very hard to do if it does not follow the logical form. You'd have to test a bunch of stuff. All right. So an example would be P implies Q as a premise. You've got not Q. What would be the appropriate conclusion here? Well, this actually follows the form of the logic of the contrapositive, and so the correct conclusion here is not P. Uppercase would be a set. All right. Here we have P or Q. You have not P. This actually follows the form of the disjunctive syllogism, right? And so I've got the or, and so here I've got the Q, right? So that would follow from the standard forms. And so now in these last few minutes, I'm going to have the Euler diagram and the syllogistic arguments. And I'm going to set this up, and then we're going to do some examples. So this section presents another form of argument called a syllogistic argument, better known by its shorter name, syllogism. And so the validity of a syllogistic argument is determined by using Euler diagrams, as is explained. So syllogistic logic is a deductive process of arriving at a conclusion, and it was developed by Aristotle in about 350 BC. Aristotle considered the relationships among four types of statements that follow. And you'll recognize that those four statements are the quantified statements from chapter 2. I'm sorry. And so this is the difference between the symbolic logic and the syllogism. We must deal with the quantified statements differently. And so how? Well, I got to do it with Euler diagrams. And so what we have here are, hey, all A's are B's. How would I draw that as a Venn diagram? Take a second. And hopefully you came up with this, right? A would be a subset of B, all right? And then if an element is in A, then that element is also in B, right? And so that's this, okay? Now what about no A's or B's? How would I draw that Venn diagram? Take a minute, think about it. So hopefully you came up with this disjoint picture where if an element is in set A, then it is not in set B. And you can see that element has no possible way of being in B. All right. So now what about some A's are B's? How do I draw that as a Venn diagram? Well, hopefully you can figure that out. And hopefully what you came up with was this picture right here, where there is at least one element that is in both set A and B. And that element right there is in both set A and B. And so how do I do some A's or not B's? Right? So think for a minute. And hopefully what you came up with was there's at least one element, this guy right here, that is in set A, right? So here's set A, that's an element of it, that is not in set B, right? And so that's how you would draw that. So those are our four quantified statements with their Venn diagrams, right? So to determine whether the syllogism is valid or not, we construct the Venn diagram corresponding to the premises. When we do that, we are constructing an Euler diagram, being a very specific form of Venn diagram. Begin with the first premise and work your way down. Okay? Hint, try to make it false. Right? In other words, if you have a choice about where you place a set or an element, try to place it in a way that makes the conclusion false. If you cannot, it's probably valid. If you can't do it that way, it's probably valid. Alright? And so, now what we need are some examples. And I'll do those in the next video, and that makes us happy.